Hey guys, how's it going? Welcome back to the channel. So today we're gonna be going through distributed transactions. So I feel like distributed transactions are also one of the complex systems that one could build in software engineering. Um, so especially if we look at them from a microservice perspective. So before we get into too much detail, I just wanna say we can think of like a transaction as a group of action that should be performed as if they were single bulk action, right? So if you look at something like an e-commerce, right, whereby a user has to make an order, right, and then we have to build that user. Everything has to like happen. If we can't, like, let's say make an order but we did not build the user, or maybe build the user but we did not actually record that order in our database, there will be a lot of data inconsistencies in our system, so we don't want something like that, right? So we didn't have this problem, um, the complexity, I mean, we didn't have the complexity of like distributed systems when we were working with monolithic architecture. So you can think of a monolithic architecture as an architecture whereby we have a single database, right? And like essentially the user makes an order and it goes to our backend and we start our transactions. Could be updating the balance, could be updating the order, then we commit. Essentially we get this thing called atomicity from the ACID. So everything happened in one go and it becomes successful. If one thing fail, like if the balance fail, everything fail, right? So that's that. Now what happens when we go to microservice? So when we go to microservice, essentially we have like services with their own database. For example, this could be an order. It has its own databases, right? This is a payment system that is used to bill the customer, and it has its own database, right? But let's say we make an order for this customer, right? And then for some reason, for this system goes down, or maybe there is a network issues, and we don't get to bill the customer. But in this database, we have recorded that this order has happened, right? So we start to have data consistencies. If we take a look at this from a simulation perspective, we could be having an orchestration system. So orchestration system is the one that actually calls these services, right? For instance, it's going to start with number one. It's going to make sure that, okay, we check the customer balance. Okay, this customer balance, they have enough funds and I'm going to bill them. Yes. Then now it has to do step number two, which is to create an order because the customer has funds. But then for some reason, the service is down, the database is down. This becomes a problem because now we have already billed the customer, but there was no order. Okay, so that ACID is gone. So it all comes down, if you can think about it, all comes down to data consistency. So because of this, maybe you must be thinking that, okay, if then that's the case, why not then create one database, right? So these services, they can all write to a single database. For example, we we build a customer, we record this, and we make an order. We have one single database. So within that work, that could be a possible solution, yes. But it then uh it then take us back because one of the reason why we use microservices is because of the advantages to enable us to be able to make deployment much quicker. So we can think of like we have a single service which is easy to deploy and it's not dependent on other services. So it's its own separate thing. And given like the scale at each some of these companies, there's so many teams, so this team are working in separate. So all of these and all the advantages that has to do with microservices, I'm not going to get into much of them, but that's the idea essentially. But the point that I'm raising is that if you're going to have the single database here, you will be losing those advantages, right? So what could be the possible solution then? So in the industry, we have like came up with like certain solutions. The first solution that we thought about was the two-phase commit. So you can think of a two-phase commit as like we have a client, right? And we still have our orchestrator, which makes that API calls. But now we introduce this thing called coordinator. What is this? This thing is a coordinator, so it has this prepare and commit state. So what it does is that each and every time a user makes a request, right, it creates a transaction in the database, right? So you can think of like it goes to the table and it creates an order. For example, transaction one. Then what it does is that it calls the customer funds. This is called the prepare step. It prepare by making sure that okay, do we have enough funds here, right? This service will return yes, okay. Then it logs okay. It does not commit it yet. It has to finish calling all of the services. It goes to the order. Do we have enough product? And can I make this order? Then the order returned yes. Then it returned okay, right? Then the final step is that it will then send this thing commit. So it kind of like give us that atomicity. You can tell that all these transactions are all happening in all one go, like in sequential order. And the good thing is that if the customer did not have the funds, right, it was gonna fail the whole entire operation. So it gives us that atomicity, right? So that's how it works. However, you could have realized this also. The problem with this thing is that it's more like a sequential thing. So you make this order, then you have to wait. So if like the network bandwidth is bad, then you can see that the latency of the application is gonna be compromised, right? Because you have to wait for each request to go up and down. So you're gonna be compromising the system from that perspective. And the second thing that you can think of is that the coordinator also can become a bottleneck, can become a single point of failure. So if it goes down, what will then happen? Okay, I spoke about latency and throughput, which is I think they're being compromised because now you have to wait all of these services, especially if like you have like a lot of services. We only spoke about order and payment, so you have like cart in an e-commerce system, right? So things get very, very complex. So there was another technique that was introduced called the saga pattern, right? So essentially, you can think of the saga as like we try to make requests to each service, and each service, when it's done, it then omit an event to a message queue. For example, let's say here we made a payment, then we'll log an event in this message queue to say the user has enough fund, for instance. Because of this is a queue, all the consumers that are subscribed to this queue will be automatically called that, okay, hey, someone has made a payment. Can you please create an order? The service will then create an order. It will then check if like we have a product, for instance, right? Then it will make an order, something like that. But if we do not have a product, it will then omit another message to say, okay, there is no product, so I can't make this order, right? This service will call subsequent services to make sure. So, but the point here is that you can think of a saga pattern as each local transaction publish domain events that trigger local transaction in another services. It's synchronous, and this is a bottleneck because what happened is that if we have like thousands and thousands of services, right? I think it was Twitter. Twitter has like 1,000 service. So like, one service calls another services. Like Elon Musk said, the RPC was making like 1,000 request, something like that, right? So, but the point that I'm raising here is that you end up having these requests, right? Like going on and on in a sequential order. So might that be a bottleneck? I've seen a lot of people who overcome this problem, but still using the saga pattern, right? So that's that. What can we do then? We can go back to accounting because we're working with money. We want to make sure that transaction is all about when we're working with like all of these transaction based services like e-commerce, right? So, but the point here is that how about we have this thing called a similar thing called reconciliation from accounting. So, what do I mean by that thing? So, I'm saying that we can think of this as like we have a service, right? Um, let's say a client makes an order, which is step number one, right? We record this as number two in our database, right? We call the balance service to say, okay, we've made an order. Can you please bill the customer? And the balance or payment service then bill the customer and it records that amount for us, right? So then this balance has to then send this guy to say, I have billed the customer. Can you please change the status of the payment there to say paid, something like that. So you can think of that here. We have a column called um, status. So here, maybe when we make an order, step number two, we can say order issued or something like that. Then when we make a payment, we have to come back and say, okay, we have paid this, right? If it happens that this service goes down, if it happens that this service stays down, then we do what we call, like I said, reconciliation. At 12 midnight, what we do is that we try to get all the statuses which have not been paid. We get all of them. We try to reconcile them by making sure that, okay, an order has occurred, we made a payment. Can we change their status to paid? Right? And we make sure that everything just matches. That's one way we can go about it. Right? So from an API perspective, how will that look like then? Now we can have a get from order, then you can have a paid, which is false, right? Then you go to paid, say this, you say this order, I wanna make a payment, then you go and change that status to paid. That's how from an API perspective, this thing will probably look like. So, but this thing does not scale well, especially if you have many services. So because like you can see from this service that I spoke about, so you're going to make a lot of requests, right? You have to make an order to balance, then balance still has to go back to make an order and order. And you can think like we have multiple services, so it's going to be back and forth. So we don't want anything that slows down the system. We still want to get that ACID, right, and data consistency, but we don't want to like also like have a slow system at the end of the day, right? So I'm going to introduce you to a new concept also, which is CDC data. You can think of this as the capture data, change data capture. So essentially we can think of this as like we try to say we replicate the changes that have happened to our database to another database or maybe another stream services, another downstream application, right? So the point that I'm talking about this is because if we take a look at let me zoom in, sorry about that. If we take to look at this use case is that we can think of like with a client, then we have a business logic here. If we make an order, right, to this database, then we're gonna replicate that order to not necessarily replicate, but literally we're gonna replicate in another database, or maybe have that data goes to another database. So we use this thing, change data capture, and it's gonna go into our balance, right? So that's what it works. So one process change in one DB. So, however, this can get us halfway. It's not a bad solution, right? I think it's still a good solution. However, the problem is that because every time the changes happens here, we have to replicate them inside here. This is done by this system called change data capture. Isn't that gonna slow down the service, isn't because we're making how many requests every time we have to do that, right? So this might slow down the service. So there is these two methods uh, for CDC. There's one called query based, and there's one called log based. So this is the one which is preferred because it has low latency. We're using the log, necessarily the transaction log, to replicate any actions that have happened in the DB. So this one is quite, it's going to slow down the DB because every time we have to make a query based on the changes that have happened. So usually we prefer to use the log-based transactions, right? But this one comes, the downside of it is that it's quite, it's quite complex to build. So there are some commercial CDC that are out there, but yeah, there's an open source version of it you can use. But that's a trade-off that you can think. But one thing is that the advantage is that you don't have to get to disturb the database in production. So you just do all of these changes and you replicate them. But the problem still arises, which is, what if now, yes, this database goes down, right? So we are replicating the changes, yes. Maybe but the log, we can get the history of the transactions. So we can always recover them in the log, right? So, but there's also a clever way of doing it, because I think database always go down and it always die and come back. But anyway, we're gonna get into that solution. So essentially, CDC eliminates the need for DB for the need for multiple DB for states, right? We don't have to think of having multiple database to capture that. You can always replicate the changes across all the databases. So that's the advantage of CDC. Okay, so I really like Confluent example that they've given us here, because I think including Kafka into the CDC solution can actually make this solution more robust than it is just alone. So essentially, Kafka can actually allow us to also stream the changes in the DB to a topic. Another thing that we can think about this is that Kafka, we can have many consumers of the DB getting the data from Kafka or something along those lines. So we can make a message queue also to be our source of truth. By that, I mean, if a client make an order, right, we can then commit that order to an event stream. Then that event can be consumed by the order service and all other respective services that are connected to, that are consumer to the message queue. So if a service, for example, the payment service, process this order that has been made and it makes a payment, it has to commit an event also to say that, okay, the customer has been billed. Then this order is gonna get that event. It's gonna change the status to something like paid, something like that. But the point here that I'm making is that we have one single source of truth. Everything goes here, and all the services reports here, everything that is happening. And so I think this could be a very good solution if we think about it. So service updates their state based on these events that have been omitted here. Okay, so that's like that. I think that's like all the solutions that are out there, and some people are implementing it. I'll leave the link to some of the sources that I found. Thank you guys for tuning in. I really appreciate it.